Welcome to the second part of our introduction to acids and bases. In the last part, we looked at the Arrhenius theory for explaining what an acid is and what a base is. And the Arrhenius definitions of acids and bases basically meant that acids contain the H plus ion and bases contain the hydroxide, the OH minus ion. But we also saw how the Arrhenius definitions can't explain the case of ammonia, because ammonia doesn't contain OH minus. So in this lesson, we're going to look at two further explanations of acids and bases that are going to give us a more complete picture of what they are. And that brings us to the Bronsted-Lowry theory. These are two scientists that worked on acids and bases and came up with this definition basically independently in different places, but they came up with it at about the same time, so we credit both of them with this understanding of acids and bases. And before we talk about what they actually said, it's important to recognize that the hydrogen ion is simply a proton. And that should make sense, because a regular hydrogen atom is simply one proton with no neutrons and one electron. So if it loses an electron and gains a positive charge, all that's left over is a proton. So having said that, Bronsted-Lowry came up with the definition that an acid is a substance that donates a proton. So it's an H plus donor, or a proton donor. A Bronsted-Lowry acid is some substance that donates a proton to something else. And that means that a Bronsted-Lowry base is a H plus acceptor, or a proton acceptor. Because if some substance is going to give away a proton, another substance has to accept it. Another substance has to accept it. So let's look at hydrochloric acid. We know that's an acid. We looked at that in the Arrhenius definition. Let's see how it's a Bronsted-Lowry acid as well. The Bronsted-Lowry explanations explain every acid that Arrhenius could explain, but they also explain a few more cases of acids and bases that we'll look at. But let's start with HCl, which we know is an acid, and we know works with the Arrhenius definition. We know that when we put the hydrogen chloride in water, it's going to ionize, and it releases H plus into solution and Cl minus into solution. But this isn't actually the full story. This hydrogen ion does not stay alone, because there's another substance involved here, and that's water. And there's actually an interaction between the water and the H plus ion. So water can combine with an H plus ion that's floating around and form the H3O plus ion. We call this hydronium. So what that means for us is that when HCl combines with water, or is placed in water, you actually get this hydronium ion in solution and the Cl minus ions. If I draw some particle diagrams now, we're going to see this Bronsted-Lowry theory in action. So we're going to make H is green, we'll make the oxygens red, and I'll make the chlorine orange. And so here are the particles shown. So what has to happen to get from our original reactants to this hydronium ion and the chloride ion is that the hydrogen on this hydrochloric acid basically gets attracted to this water molecule and temporarily joins it to make this hydronium ion. That leaves the Cl ion by itself, which is right over here, and means that water has an extra hydrogen now, making it into the positively charged hydronium ion. Now, this H plus that gets transferred, that's just a proton. Here's our definition of the Bronsted-Lowry acid. It's a proton donor, and the HCl is essentially donating a proton to the water. So this is a proton donor, which is a Bronsted-Lowry acid. Whereas the water molecule is accepting the proton. It's becoming the hydronium ion. So this is a proton acceptor, or a Bronsted-Lowry base. So that's great. We've confirmed that HCl is an acid. There was really no question about that from the Arrhenius definition. What we had a question about was how ammonia is a base. So let's look at ammonia reacting with water, and let's see how that's a Bronsted-Lowry base. Let's look at the reaction of NH3, ammonia, in water. If we put these together, we're going to see that it becomes NH4 plus, the ammonium ion, and the hydroxide ion. So here we have the hydroxide ion being produced, just like Arrhenius said. But the NH3 is not ionizing to do it. The OH did not come directly from the NH3. It doesn't contain hydroxide. So how did hydroxide still end up being made? Well, you can see that between NH3 and NH4, it had to gain an H plus. And that H plus had to come from the water molecule. So when water gave up a hydrogen, it became the OH minus ion. and that hydrogen went to NH3 and made it NH4. So that makes this a proton acceptor, which is a Bronsted-Lowry base. And in this case, the water is a proton donor. So we would say that NH3 is a Bronsted-Lowry base, and that H2O in this case is a Bronsted-Lowry acid. Now there's two important terms we should know here. When the NH3 accepts the proton, it becomes NH4. So NH4 has a special name. We call it the conjugate acid. So NH3 as a base, after it accepts the proton, becomes what we call a conjugate acid. And similar to that, water, in this case the proton donor, the Bronsted-Lowry acid, is going to become OH- after it gives away that proton, which means that the OH- on this side is called the conjugate base. So H2O was the acid, and it becomes a conjugate base after it gives away the proton. So these two pairs we just identified, NH3 and NH4+, and H2O and OH-, these two pairs are called conjugate acid-base pairs. And it's important to be able to label the conjugate acid and conjugate base given a reaction like this. The conjugate acid is always going to be the substance formed when the base gains an H+ ion, or accepts the proton. And the conjugate base is always going to be whatever substance is left over when the acid, or the proton donor, loses the H+ ion. We've now looked at a Bronsted-Lowry base in NH3 and a Bronsted-Lowry acid in the HCl earlier. And there's one more thing I'm going to point out that's pretty interesting. And that's the role of water in both of these equations. In this one, with NH3, when water was with a base, water acted like an acid. We labeled it as a Bronsted-Lowry acid because it gave away a proton. However, if we look back at our HCl example, in this case, water gains a proton, it gains an H+ to become hydronium, and it was a proton acceptor. So in this case, it was a Bronsted-Lowry base. It acted as a base when put with an acid, HCl. So in one example, we have water acting as a base, and in the other example, we have water acting as an acid. And so water is actually an example of a special substance that we describe as being amphoteric. And an amphoteric substance is something that's able to act as an acid or a base. That wraps up our introduction to acids and bases. As you've seen, the Bronsted-Lowry theory is a more general theory than the Arrhenius definitions. It explains more cases than Arrhenius can. And it's also true that any Arrhenius acid and base is also a Bronsted-Lowry acid base, because Bronsted-Lowry is more general. There's actually a third, even more general definition, and even more thorough definition, called the Lewis theory of acids and bases, and that's what we're going to look at next. So keep watching for that. Otherwise, write down any questions you have in your notes and bring them with you to class. The Lewis theory of acids and bases, unlike the other two, has nothing to do with the H+ ion. It instead examines what's happening to electron pairs. And it's true that it's not totally unrelated. It's kind of like looking at the same situation from a different perspective. But this perspective is even more general than the other two cases, and explains the actions of more substances that are acids and bases. We'll start by comparing this to the Bronsted-Lowry acid and the Bronsted-Lowry base. We said the first of these was a proton donor. The Bronsted-Lowry acid is a proton donor, whereas the Bronsted-Lowry base is a proton acceptor. You may start to see how this is simply looking at the same thing from a different perspective. In one case, I'm donating a positive ion away, and from the other perspective, I'm accepting a negative electron pair. Let's start by looking at two things we know are acids and bases. We'll use HCl reacting directly with NH3. Independently, we've shown these are both acids and bases. And when they react together, they form the ammonium ion and the chloride ion. So we have HCl like this, and we have the NH3 molecule, a nitrogen with 3 hydrogens coming off of it. And it also has a lone electron pair left. So by looking at the reaction, we can see that the Cl that was part of HCl does end up by itself over here to Cl-. So that means that this H is going to travel to the NH3, and that's where we get the NH4 from. Now remember, the H, when it travels over here, when the H leaves the Cl, it's really coming as H+. It's coming as a hydrogen ion, not as a hydrogen atom. So this H+ wants to get some electrons. It's going to be attracted towards these electrons on the nitrogen. So when it finds these two electrons and it becomes the NH4 ammonium ion, we say that the H has accepted electrons from the N, and that the nitrogen has donated these two electrons into this bond with that H that just joined it. So NH3 is acting as an electron pair donor, the Lewis base. It's donating its electrons to this H+, and the H+ came from the hydrochloric acid. So that's accepting the electron pair to form this bond. The hydrogen is accepting the electron pair. So that makes it a Lewis acid. So doing this just confirms that HCl and NH3, two substances we knew from the Arrhenius and Bronsted-Lowry definitions to be acids and bases, also comply with the Lewis definition of acids and bases. Now let's look at a molecule BF3, boron trifluoride. And boron trifluoride acts like an acid. And when boron trifluoride reacts with a free fluoride ion, we get the BF4- ion. So let's draw these two molecules and see what's happening. Here we have the boron trifluoride molecule. It has 3 fluorines coming off the central boron. And we also have the fluoride ion. So this has an overall negative charge because fluorine should have 7 electrons and this one has an extra one, giving it 8 valence electrons. Now for boron to get to 8 valence electrons, it only has 2 in this bond. Here's another 2 and here's another 2 for 6 total. But it can accept 2 more electrons to get to 8. And those 2 electrons are going to come from the fluoride ion. So this pair of electrons is going to be shared with the boron. So in this case, we have boron trifluoride acting as an electron pair acceptor. So this is a Lewis acid. And the fluoride ion in this case is acting as a Lewis base. So you can see that this example has nothing to do with H+ ions at all, and yet we still have substances that behave like acids and bases. And that's because the Lewis theory allows for a more general look at acids and bases. It's a more general explanation.